Hello, and welcome to the Group 5 final presentation. We'll start with an overview of the system goals and setup. Our objective is to design an integrated energy management system to minimize the payoff period of a solar and battery subsystem installation based on appliance electricity savings. Inside the system, we include factors related to the solar panel and battery designs and home energy usage patterns. Outside the system, we've excluded factors such as seasonal and extreme weather, as they are unpredictable. We aim to solve the system-level design problem to address the growing environmental and economic need to convert to more renewable forms of energy. An optimization model will be useful to appropriately balance the needs for inexpensive setups with maximum utility savings. Shown here is our system flow diagram. The solar optimization uses average weather conditions to output usable AC power to the battery and the system cost to the payback period. The battery optimization uses AC power from the solar subsystem, grid buyback protocols, and the appliance load demand profiles to output available discharge energy to the appliances and system costs and revenue to the payback period. Finally, the appliance optimization uses the available battery energy, the grid power supply, user interface requirements, and home electrical infrastructure to output a daily appliance load profile to the battery and an electrical cost savings to the payback period. The subsystems are repeated here in a textual format. Our solar subsystem will handle energy generation, our battery subsystem will handle energy storage, and our appliance subsystem will address energy usage. To recap our linked variables, there is a two-way interaction between subsystems 2 and 3, with available battery energy being sent to the appliances and energy usage needs being sent back to the battery. This ensures that the battery is not over or under designed. Between subsystems 1 and 2, we have a one-way relationship with usable generated power being sent to the battery.
Next, we'll look at our optimization process.
Here's our optimization model structured into three respective subsystems. Starting with the solar subsystem, the key parameters include panel efficiency, cost, mass, and the available roof area. Using irradiance data of a typical year, we compute the power generated by each panel over time and sum them to obtain total solar output. Next is the battery subsystem, where we model both the economic and physical behavior of energy storage. This includes cost per kilowatt hour and kilowatt, efficiency losses, depth of discharge limits, and power constraints. The battery stores excess solar energy and can discharge to meet demand, while also allowing excess energy to be sold back to the grid. Finally, in the appliance subsystem, we model household demand based on appliance energy consumption and cycle durations. Power demand is calculated as energy divided by duration, and total cost is determined using time of use electricity pricing. We compare the cost of grid usage with and without battery to support and determine our cost savings. Together, these subsystems are linked through intermediate variables like solar generation, available battery energy, appliance demand, allowing us to evaluate system performance and optimize for economic outcomes as well as payback period.
Following up, we are manipulating 12 key design variables. These dictate our physical hardware, specifically the number of solar panels and the battery's capacity, as well as our behavioral schedule, determining exactly when our major appliances run, what operational mode they use, and whether they draw from the battery or the grid. These three subsystems are deeply coupled. Solar generation feeds the battery, which in turn supplies the appliance demand. Our primary objective here is to minimize the system's overall payback period. We do this by taking our total capital costs, factoring in a 70% rebate, and dividing them by the daily financial benefits, which include both our appliance electricity savings and the profit from selling excess solar back to the grid. However, we can't just maximize hardware to get more savings. The model is bound by several strict constraints. We have physical bounds, like a 2,000 kilogram roof mass limit and a 48 kilowatt instantaneous power limit. We also have logical and user rules, such as ensuring the washer finishes before the drive starts, alongside strict budget caps. Ultimately, this model is a complex balancing act. More panels and a larger battery increase our savings and grid profits, which lowers the payback period. But finding the perfect system size means balancing those aggressive savings against their strict mass, budget, and power constraints.
The modeling was divided into three analytical subsystems: solar, battery, and appliance usage. The solar model uses irradiance data, roof geometry, and panel properties to calculate hourly solar generation and solar capital cost. The battery model takes in solar generation and appliance demand, then applies charging and discharging efficiency, depth of discharge, and battery limits to estimate available storage energy and sale profit from exported power. The appliance model uses the dishwasher, washer, and dryer schedules, operating modes, and power source selections to build the demand profile and calculate electricity cost savings. Key assumptions include a fixed roof tilt, constant battery efficiencies, fixed appliance energy and duration by mode, and known time of use pricing. These assumptions kept the model simple enough to solve analytically in MATLAB while still capturing the main subsystem behaviors. The optimization was performed in MATLAB using a genetic algorithm with an IDF formulation. The process starts by defining the design variables, then running the solar, battery, and appliance models, computing payback together with a mismatch penalty, updating the design with the genetic algorithm, and repeating until the best design is found. Subsystem coupling is handled through wide-tilt variables, which represent battery availability and appliance demand. Instead of forcing exact agreement between subsystem outputs at every step, consistency is encouraged using a quadratic mismatch penalty in the objective. A genetic algorithm was chosen because the problem is nonlinear and includes both continuous and discrete integer variables, making it a good fit for combined sizing, scheduling, and operating mode decisions.
Finally, we'll look over the results.
In order to evaluate the robustness of our system, it's important to consider a range of settings or conditions in which the optimization model may be used. Our first run is a baseline with average values set for all constants and parameters, which resulted in a minimized payback period time of 9 years and 10 months. In run 2, we assumed the homeowner may want to consider a setup that is very small, with low specifications but that costs less to install. With this change, we see a reduction in the payback period because the total cost of capital has in fact decreased. Runs 3 and 4 consider changing the costs for the grid energy, which will help the owner understand how their system may be better optimized if they're expecting significant rate increases or decreases in the future. Increasing the grid costs led the system to optimize the amount of solar generation in order to maximize the profit that could be made by selling this excess energy back to suppliers. The fifth scenario represents households who have more strenuous appliance usage needs, so their payback period is actually lower because the amount of money they save by using a battery instead of a grid is higher given the higher energy demands of a heavy cycle compared to an eco or a normal cycle.
Sensitivity analysis. We performed a sensitivity analysis to evaluate how key system parameters affect our overall performance objective. A hybrid approach was used, applying a 10% perturbation of continuous variables and nearest neighboring changes for discrete variables. The 10% change was used to normalize comparison for across variables with different units. We selected one parameter from each subsystem: irradiance for solar, grid price for appliance demand, and depth of discharge for battery, since individually had high impacts on their subsystem independently. From the analysis, the most sensitive constraint is irradiance data, since it limits on-site generation and directly impacts power availability and source selection. The most sensitive parameter is grid price and appliance demand. As shown in the table, reduction in solar availability and battery capability increases payback and grid use, but changes in demand and grid price produce the largest overall impact on system performance. Overall system performance is most sensitive to demand and grid price, which drives energy requirements and total grid reliance cost.
We are validating the result against real-world benchmarks compared to typical residential systems. Our model predicts a payback period of about 2 to 10 years, which is lower than the usual rate. This mainly comes from limited demand modeling and simplified economic assumptions. For grid import, our system also shows lower values compared to the baseline, since we only consider appliance level loads, so total demand is much smaller than a full household. Solar generation is within a similar range to real-world values after applying constraints, although it remains sensitive to cost and demand assumptions. The biggest discrepancy is in battery capacity. Compared to typical systems, our model consistently selects much smaller batteries, indicating that storage is not economically attractive under our current setup. Overall, while our results follow reasonable trends, the difference highlights how strongly the model is influenced by demand assumptions and cost structure. Comparing subsystem optimization with the full system approach, subsystem optimization treats each part independently, so it tends to give locally optimal solutions. But with the IDF formulation, we start capturing interactions between solar, battery, and appliance demand. That said, since we are using a penalty-based method, the coupling isn't perfectly enforced, so some inconsistencies can still appear. From an engineering perspective, the system behavior is mainly driven by demand and cost. For example, when grid prices are high, the system tries to rely more on solar and battery, but under heavy load, it still ends up using the grid because the battery capacity is relatively small. So overall, since we only model appliance level demand, the system naturally favors solar over storage. For future work, we will improve model fidelity, include more realistic loads like HVAC and EV charging, and refine the economic assumptions to better match real-world behavior.
Thank you for listening. Please feel free to reach out if you have any questions or feedback.